Hello, good afternoon, everyone. My name is Daniela Rus. I'm the director of MIT's Computer Science and Artificial Intelligence Laboratory, and I want to welcome you to our Dertouzos Distinguished Lecture Series. Today, I am delighted to introduce our guest, Professor Dorit Aharonov, who's coming to us from the Hebrew University in Jerusalem. She's also a CFO of Kedema Quantum Computing. This is a startup she co-founded in 2020 to build the operating system or the control system for the quantum computers. Dorit received her PhD degree at the Hebrew University of Jerusalem and then had postdoc research at Princeton and Berkeley. In her PhD, she proved the quantum fault tolerance theorem, and this theorem is one of the main pillars of quantum computation today. Her research can be viewed as creating a bridge between physics and computer science, attempting to study fundamental physics questions using computational language. Now, for her work, Dorit received many accolades. In 2005, she was featured by the journal Nature as one of the 4 theoreticians making waves in their chosen field. And in 2006, she won the Krill Prize, and in 2014, she was awarded the Michael Bruno Award. Now, besides quantum computing, Dorit's other passion is body-mind processes, and in particular, martial arts. For the past 18 years, she has been practicing and studying Tai Chi, yoga, and Kung Fu, and in addition, has recently become a teacher in the Feldenkrais method of self-improvement and awareness through movement. Her TEDx talk, which I watched last night, on achieving one's full potential, introduces 4 principles she has learned in her practice of body-mind methods and discusses how these principles can be useful in doing scientific and mathematical research, suggesting ways to overcome any obstacle with less force. So this ought to be useful for all the students and the faculty in the room. I greatly admire Dorit's ability to be such a brilliant and visionary thinker in computing while maintaining so many human-centered interests. We're honored to have her today and to hear her thoughts on quantum computing and how this will impact society. So let's give Dorit a very warm CSAIL welcome.
Wow, thank you so much for this introduction, Daniela, and for this invitation and for the opportunity to give this talk. So let me say that, first of all, let me say I have no idea how quantum computing will affect society. But I want to tell you today about some question which I think is extremely important from the point of view of where quantum computation will go and what we know about it today, and possibly how we should think about it in ways that might affect the progress in quantum computation itself. And we'll talk a little bit about how these things are related to implications and stuff like that. Okay, so basically, in order to start talking about why quantum computation is interesting, one has to talk about computation. And so the computational power of physical systems is basically, one can understand them by modeling a variety of, providing a variety of computational models that you can see here. And a very important statement in classical computation is the extended Church-Turing thesis, which was phrased by Bernstein Vazirani in '93 to say that all physically realizable computational models can be simulated in polynomial time by a probabilistic Turing machine. So basically, the reason why this is so important is that it basically says that all these beautiful models of computation are more or less the same when you look at it in the right resolution of up to polynomial overheads. So when I try to understand whether a function is difficult or not to compute, it doesn't really matter which model I'm looking at, okay, up to polynomial overheads. So this is the essence of the extended Church-Turing thesis. Enter quantum algorithms. And quantum algorithms, well, they seem to provide a very strong challenge to this thesis. From the factoring algorithm, famous Shor's algorithm, and quantum simulations, to Pell's equation, Jones polynomial, and quantum walks, and to current algorithms such as, I don't know if those acronyms mean anything, but HHL, QAOA, VQE, these are variational algorithms of parameterized circuits attempting to optimize various problems, and to topological data analysis. So all these seem to provide really very exciting promise in a variety of implications, from pharma to finance to fertilizer production to material design, and you can go to sound really, really pompous, that might just save the planet. So maybe there's a little bit hype in this topic, but this hype should not actually prevent us from really realizing that there's a true promise in quantum computation and in its exponential, the potential exponential advantages. By the way, feel free to raise your hand and ask questions or make comments. I like interactions, as you'll see in the talk. Okay, so what does this mean in terms of the extended Church-Turing thesis? So you can see that essentially, okay, so BPP is the class of problems solvable in polynomial time by classical computers. BQP is the class of problems solvable in polynomial time by quantum computers. And these problems with supposedly exponential advantage sit in BQP but are not known to sit in BPP. And this hints, or this provides, so this leads us to believe that quantum computers violate the extended Church-Turing thesis, or will violate them. But if you look a little bit into this statement that the extended Church-Turing thesis is violated or will be violated by quantum computers, this actually breaks into two. So one of the two parts is that we strongly believe that BQP is strictly larger than BPP. And this is a mathematical conjecture. It has nothing to do with physics. These are two models. Whereas the other thing is that quantum systems can, in principle, physically implement BQP. Okay, and this is not a mathematical statement. This is sort of a physics statement that we can actually implement this model of quantum circuits. And so this relies very strongly on the invention of quantum error correction. And the reason this is important is because in any physical realization, we will have noise in the system. So there's quantum error correction and the discovery of quantum fault tolerance, which basically tell us that under some assumptions on the noise model, we will be able to implement quantum computers in reality with noisy quantum computers. And we will be able to implement quantum algorithms in noisy quantum computers. And basically, just to recall this, the statement of the quantum fault tolerance, what it says is that if the noise level in the system is below a certain critical value, threshold, below that, the system can actually maintain its exponential capabilities as if there's no noise at all, okay? So one can do error correction, and the overhead in the error correction is just polylogarithmic. And that means that the system is as powerful as an ideal quantum circuit. So this basically brings us to a point of view that is resembling a phase transition between ice and water, where essentially we basically believe, due to the fault tolerance theorem, that all these systems in which we're trying to implement quantum computers today, they will be capable of implementing universal quantum behavior. And by that I mean macroscopic entanglement in the system and the ability to control this entanglement in the system in order to arrive at these exponential overhead or advantages. And for that, we need to go below the critical point. So this is really we believe that there is a new phase of matter, sort of, if we go below this, this critical point. Okay, so this is kind of a very extravagant belief. And I should say, this is what I'm citing here is a result, a breakthrough result of 2021 by Physics World of Kotler et al., in which they actually managed to show experimentally macroscopic entanglement between two membranes, two drums. And this can be viewed as macroscopic entanglement, but I don't mean that. I actually mean something which is much more extravagant than that. I mean a macroscopic entanglement that entangles macroscopically many degrees of freedom. Here you have many particles, but the nature of entanglement is only, can be described by only a few degrees of freedom being entangled. So I actually mean that once we go below the threshold, we will reach the point where we go to the ice phase of matter. Okay, so this is a very extravagant belief. And it's worthwhile asking, what evidence do we have for that? For the belief that this is, that we will be able to do that. And this is a very important question, I think, given the amount of effort that society invests in quantum computers and the hope in that, and I think it's a very important thing to understand. What really gives us something to stand on when we believe that we will be able to build quantum computers. So 20 years ago, I visited MIT. Every time I visit MIT, I come from here with some important idea. So one visit was 20 years ago when I met Oded and Madhu Sudan in the Radcliffe Institute, and I had a very important conversation for me. And in that conversation, both Oded and Madhu asked me, basically, so I was very enthusiastic about quantum computation, and I told them a variety of things that quantum computers could do, and both of them were very skeptical, and they asked me, how do you know that this will actually be possible? And they asked me to convince them that we already have evidence. I mean, if we are by now trying to build quantum computers, we should have current evidence, not evidence that we will have once we actually manage to realize Shor's algorithm for factoring, but current evidence. So what is the evidence that we have now? And I was sure, okay, we already have evidence by simply the fact that quantum computers realize quantum evolution. Quantum evolution is something that's hard to simulate. So that should be evidence that it's the very fact that quantum evolutions evolve in nature that makes us believe that something hard computationally is going on. I went to the physics department and tried to come up with some evidence, and the more I dug into it, the more I realized there is no evidence. But there was something that I did come out of this conversation with, which is something like a statement of a challenge, which you can view as the following challenge. Come up with a computational problem, A, conjectured to be super polynomially hard for classical computers, B, that its solution can be verified, meaning that I know that I have solved it, and C, that there is a good evidence that quantum computers can solve it efficiently for large instances. Okay? Sorry?
Do actually means verified polynomial time?
No, I deliberately forgot the word efficiently, but it needs to be verified. Okay, and the thing is that it seems hard to give evidence for this. It seems really hard to give evidence for this from current experimental data. I'd like to note that when I talk about quantum supremacy or quantum advantage, there's sort of two different ways to talk about this. One is practical advantage, meaning that I solved some problem faster than what classical computers would be able to solve that particular instance of a problem, finite question. I'm not talking about that. I'm talking about the other question of asymptotic quantum supremacy, meaning scalable quantum advantage. So we're looking for evidence that quantum computers can provide quantum advantage in a scalable way, in an asymptotic way. Okay, so the talk outline would be, first of all, I want to say some things about why it's difficult to come up, what's the problem? A little bit more, with a little bit more detail. It could go into a very long discussion, but I'll just want to hint about it. Secondly, you probably have heard about Google's quantum supremacy experiments. So that could be current experimental data for quantum advantage. I want to argue in the other direction. I want to tell you about recent results in which we actually show that these tests that were run, or similar tests to those run in Google's experiment, can actually be performed by a classical computer in polynomial time. So that puts the whole direction of what's called random circuit sampling, which is the main approach the main current approach today to try to show quantum supremacy, with a big question mark. And I will end with the question of whether we can actually hope at all to show quantum supremacy in what's called the NISQ era, the noisy intermediate scale quantum computation era, in which we are not yet at the stage where we can actually perform quantum error correction. Okay, so let's start. So first of all, here's the question about the quantum simulation, or just the evolution of quantum systems. So quantum simulations were Feynman's first motivation for quantum computers, or for thinking about quantum computation. And it's now considered one of the main candidates for interesting applications before we have in the pre-fault tolerance era. And the reason is that quantum simulations, you can think of them as robust to noise because you're trying to simulate noisy systems by noisy systems. Maybe the noise is mapped nicely, so you can actually forget about correcting the noise. Okay, so this has actually become a very big area of research, quantum simulations, where you look at, this is a Hamiltonian describing some system, and you can consider mapping starting from the original Hamiltonian that you want to simulate into the Hamiltonian of maybe a much simpler system that you can control. And it's now known that you can basically simulate any Hamiltonian, any local Hamiltonian by very simple systems, even in 1D, in fact, and that works for all local Hamiltonians. And basically, the mapping goes by taking the spectrum of the original Hamiltonian, mapping it to the lower part of the spectrum in the final Hamiltonian, and this allows actually simulating all the dynamics of the system. Okay, so now there have been a lot of experiments of quantum simulations of interesting physics in large quantum systems. And for example, this is in small letters. You're not supposed to read it, but essentially, people are using quantum simulations to study physical systems that one cannot actually simulate by classical computers. So this seems to be evidence for quantum supremacy, and this is, for example, a survey which actually explicitly says that, a recent survey that says that that it argues for the first practical quantum advantage already exists in the case of special applications of analog devices. However, I want to say that this comes from, I think, lack of understanding or lack of rigorous definition of the notion of quantum supremacy. And if you try to actually go to this quantum supremacy challenge and try to track down if the requirements are really satisfied, then the answer is no. And let's actually see that more clearly. So I want to say that though experimentally complex and really extremely challenging these experiments are, though they are so they're so challenging and physically very beautiful, it is unlikely that they can be viewed as evidence for quantum advantage, for scalable quantum advantage. And the reason is this. First of all, there's no suggestion for a computational problem. basically they're used to explore physical systems, but there's no rigorous sort of definition of a particular computational problem. As far as I know, I have to say this is as far as I know, of course. And secondly, just a second. Secondly, it seems that the simulated quantity has to be robust to noise. This is because of the reason I said before. So if it has to be robust to noise, that means that it's going to be even harder to believe that the quantity that is being computed by the simulator is computationally hard. And we don't know exactly how to argue that such robust to noise quantities are hard, even less so than we do for quantities that are not robust. And thirdly, there's no verification of the outcome in those experiments. So there's no protocol for verification that is suggested. Yeah.
Could you define a computational problem given a Hamiltonian? Is it going to exhibit many-body localization or not?
Yeah, you could.
Repeat the question.
Could you define, for example, the following computational problem? Given a Hamiltonian, does it exhibit many-body localization, which is some property of the Hamiltonian? You could, but then you run, so there were no experiments that actually look at this as a computational problem in which so you have to define a complexity parameter, and the question is, what is it that you vary, and how do you actually define that this is hard? And it's getting, so as I said, you can actually dive into it, and I really challenge anyone in the audience to do that. It's not that I'm saying that it's impossible, but it has not been done. And I think it's very hard to do because of these issues. And I want to say that one particular very important difficulty, inherent difficulty here, is in the verification issue. So here is my cartoon for how a physics experiment looks like. So you have here the theoretician, and you have the experimentalist. And suppose we want to test a physical theory. And so how would you do that? Well, in the usual paradigm, you'll have a predict and compare paradigm in which you perform a calculation, you perform the experiment, and you compare. Now, if this is classical, then the dynamics can easily be simulated, so you can make the predictions. But if this is quantum, then this side of the cartoon goes away. We cannot actually perform this prediction, because not in any reasonable time, because in order to do that, we'll have to simulate quantum mechanics, and we don't know how to do that in any efficient way. The whole point is that it's hard to simulate many-body quantum physics. So the predict and compare paradigm does not work for quantum verification. And what this means is that we cannot efficiently verify correct evolution in the high complexity regime of quantum mechanics in the usual predict and compare paradigm. We have to go in other ways, and there are other ways. I'll talk about it in a second. But the point is that so far these have not been used for physical, for existing systems, except for very, very small instances. Okay, so the way to bypass this issue of the impossibility of verification of quantum mechanical many-body evolutions is to introduce, to abandon the predict and compare paradigm and introduce a new type of experiments that is completely different than the predict and compare paradigm. These are interactive experiments. This is inspired by interactive proofs. So you can think of the BQP of the prover. Instead of in interactive proofs, the prover is all powerful. Here, the prover is going to be the quantum computer, and the quantum computer is trying to prove to the experimentalist something. And if you allow interactions, then it turns out that any quantum evolution, even though it's very hard to predict, can be verified. Great. So this is the way this works is basically by a notion called quantum error correction, in which essentially essentially the quantum system is given to the quantum computer, or the quantum state is given to the quantum computer encoded inside a subspace, which is random. So the quantum computer doesn't know where the subspace is, and then somehow the interaction helps the quantum computer evolve the state in that subspace, and the verifier can actually check that really the state is in that unknown subspace. To the computer, the verifier does know the subspace, so it can check that the evolution is in the correct subspace. And if the computer doesn't work according to the plan, then it will get out of that subspace and be caught. So, yeah.
So what's the complexity of the prover as compared to the complexity of the computation? It must be polynomial, but is it like linear or?
Oh, in those protocols, it's basically linear. Yeah.
And the complexity of the verifier is to just prepare a constant number of qubits per round and measure things.
Mm-hmm. Yeah. So these are low complexity protocols, but they haven't been done, and especially they haven't been done. Oh, so I should say that in a breakthrough result by Mahadev, this was also shown to be possible even when the interactions between the quantum computer and the experimentalist are just classical, using some cryptography ideas. So this is great. So you can do efficient verification of quantum evolutions, but you have to work hard, and for that you have to basically encode the system. It requires error correction, and we don't have the abilities to do that. And in particular, for uncontrolled systems which we actually want to verify, for example, like quantum evolutions just that occur in nature without controlling them, this is not a protocol that will work. So we have to get rid of efficient verification for now, but we can still do inefficient verification. So let's modify our challenge, or let's just be more precise about the challenge, the quantum advantage challenge, in which we're looking for a computational problem. Again, conjectured to be super polynomially hard. Its solution can be verified, but not necessarily efficiently. There's good evidence that quantum computers can solve it efficiently for large instances, and it should be possible to demonstrate it on quantum computers without quantum error correction, namely in the NISQ era, in the noisy intermediate scale quantum computing era, which we're now at, before error correction. Okay, so then the question arises, do we even expect scalable violation of quantum, of the extended Church-Turing thesis in NISQ devices without error correction? I have a question. Can I see a raise of hands? What do you think? Which do you expect violation in the NISQ era before error correction? Who says yes? Who says no?
We are the optimists.
Okay. Not enough for statistics here. Okay, so I don't know the answer. But I think the real question is to define the question better. So I wanna go to the Google supremacy results. So recently there have been a lot of effort trying to come up with quantum supremacy evidence, and one of the main approaches, or the main approach, is random circuit sampling. And this is what Google did in 2019. They basically use current noisy intermediate scale devices to sample from a random quantum circuit and perform some statistical tests on it, and then claim that it cannot be done by a classical computer efficiently. And this had been done both by Google and by University of Science and Technology of China on up to 60-something qubits. And they're really beautiful experiments, amazingly technically amazing experiments. But they might provide finite advantages, but I'm going to discuss again only the asymptotic issue. Are these experiments evidence for scalable violation of the extended Church-Turing thesis? And so, okay, so just so that we know what we're talking about, this is the random circuit sampling problem. You have a circuit, and you have, these are the gates. Time goes in that direction. These are measurements. And each qubit undergoes a certain error with probability p. P is some constant, or probability eta. Eta is some constant. And you can think of each qubit to be replaced by a completely random qubit, a qubit in a completely random state with that probability eta. Okay, so we sample a quantum random circuit C on n qubits with depth d. We fix the circuit, and we do that. We obtain m samples from the noisy distribution. That is, we run the circuit on a real device. We sample. We get some distribution that is the noisy distribution. So I denote it like this p tilde here. I get an x. I get mx like that. I perform some statistical test on those, which might be very complicated to do, might be highly inefficient. And that's it. And this is the test, and this is the test that also a classical computer would attempt to do. And we would like to compare the performances of the quantum and the classical. Okay, and I don't know if I want to go into the details of what kind of tests people use, and especially Google used, but just maybe very, very quickly, this is known as the cross-entropy benchmark test, where one actually looks at the average with respect. So this is the outcome probability of an output state x with respect to the given quantum circuit C. And you want to average these outcome probabilities with respect to some probability distribution q of x. And it turns out that if the q is completely uniform, this turns out to be equal to 2 to the minus n. And if this q is determined by the quantum circuit, it turns out to be just 2 times 2 to the minus n. And really the goal or the test is that you're able to do something slightly better than 2 to the minus n. Okay? And there are various reasons to believe that this is a hard task. Again, I don't want to go into the technicalities, but there is something called anti-concentration, which says that if the quantum circuit is random enough, then we will have this property. And anti-concentration means that essentially the expectation of this value is roughly what it is expected for the uniform distribution. So it turns out, if you didn't get what I just said, forget it. All I wanted to get from this slide is that it turns out that there is some test, and there are reasons to believe that it's hard, and it's based on something called anti-concentration. Okay, now there were already doubts cast on the hardness of this in a paper in 2021. And what we show in this result is that was done I don't know, last year, is that basically no matter what the test is, essentially a classical computer can beat it. So let me read it. Assuming anti-concentration, meaning assuming that the random distribution over the circuits is such that it's sufficiently random, essentially, there's a classical algorithm that on input, a random circuit C, on n qubits, outputs a sample from a distribution that is epsilon close to the noisy output distribution of the noisy circuit in total variation distance. And the success probability is at least 99% over the choice of the circuits. And the time it takes is polynomial in both the total variation distance, epsilon, and the number of qubits. Okay, so basically the upshot is a classical computer can approximate in total variation distance what the quantum computer does. Okay, and the point here is, well, if we have m samples, if the test is going to run m samples, then our algorithm, our classical algorithm, will take polynomial in m and in n time to produce, sort of to mimic those m samples, such that it is impossible to statistically tell between the two. Okay, and the way this is done is basically by choosing this epsilon to be roughly 1 over m, so then no statistical test can tell the difference. Yeah?
Which output distribution are you considering in this theorem? You say for any noisy, for any, like,
I'm saying for the model of noise that I told you about before, no matter, so I'm running the circuit and I'm measuring in the computational basis and I'm getting an X. So I get many samples. No matter what the test on those X's is, I can mimic it. And the reason is because I basically can mimic the output distribution of the circuit. So you give me a circuit, I can mimic the output distribution of that circuit if you add noise to it.
This depends on the noise in the.
This depends on the noise. Importantly, it depends on the noise. We're talking about a noise model in which every qubit is replaced by a completely random qubit with probability eta.
And as long as eta is positive.
Right, and this works for any eta, any positive eta.
Sorry, just to clarify, if the noise model was totally wrong, if Pauli noise is not the correct model, these two, the classical and the quantum algorithms on the previous slide, they could differ wildly?
Yeah. So you could think of possibly very unrealistic noise models in which the entropy doesn't grow in the system, for example, and then this is unknown.
And does this certify the noise model as the right noise model?
Good question. Okay, so just to say, there's a sort of a sweet spot of the depth d of the quantum circuit. The depth is sort of the number of layers in the quantum circuit that is very important because on one hand, anti-concentration, this important property that we didn't get into, it requires the depth to be at least log n because below that it's just not random enough. On the other hand, we showed only very long ago that if the depth is too large, since the information decays exponentially, so we show that the information decays exponentially with the depth, it just approaches completely uniform distribution too quickly. So after log depth, you just cannot distinguish between uniform and anything else. So basically the distribution is too close to uniform. So in order for this to be meaningful, you will need to sample at least exponential in d samples in order to distinguish between that and even from the uniform distribution. So for that to be efficient, you have to require that d is at most log n. So there's a sweet spot in which basically we're talking about log depth quantum circuits. Okay, so some remarks about this result. The running time is polynomial, as I said. Currently, it's impractical. I should say previous work has already shown, but it was very hidden and not realized at the time, that we can do that not in polynomial time, classical polynomial time, but classical quasi-polynomial time. And we strongly build on this beautiful work. And basically, the upshot is that this is very strong indication that noisy random circuit sampling cannot be the basis for finding evidence for quantum supremacy. I want to give you maybe two slides of how the proof works, just in terms of the idea, because maybe that would resonate with some of you. Okay, so this is how one would like to do simulation of quantum computation. This is what's called the Feynman path integral, where you basically write down the unitaries appearing in the quantum circuit, and you stick in sort of all the different possible strings that the unitary can take you to. And you get exponentially many paths, and you might think that you will be able to simulate by just going over all the paths, but there are exponentially many of them, so that's going to be impossible. And the noise doesn't seem to reduce the number of paths here, the number of relevant paths. So the key in the proof is basically to move to what we call Pauli Feynman path, where we work in the Pauli basis. So basically, instead of writing the probability as a sum over transition between strings to other strings, we write the operators. We move from vector basis to operator basis, and we write it as moving between Pauli operators to a different Pauli operators. So we look at Pauli operators acting between the layers of the circuit. And we consider sort of the transition from Pauli to Pauli to Pauli to Pauli. And it turns out, and I'm not going to go into the details of this, but just saying that for every Pauli path, we have sort of a Pauli coefficient here. And so for every Pauli choice here, you have some coefficient here, and you have exponentially many of them. And the key point in the proof is that the depolarizing channel, the channel in which, with probability eta, you replace the qubit by a completely random qubit, that takes every Pauli and replaces it, multiplies it by a factor of 1 minus gamma. So it creates a decay. So in the Pauli basis, essentially there is decay with the weight of the Paulis, as long as they're not identities. So what happens is that essentially if you write the description that I wrote before and insert the noise operator, it just introduces an exponentially decaying term as a function of the number of non-identity terms in the Paulis. And so there is a decay, and that means that we actually need only to go over all the Pauli path with small weight. And that's roughly the idea of the algorithm, and I'm not going to go into more details of this. Okay, there are lots of caveats to this result, so maybe I'll defer that to later, to the questions. But this roughly tells us that it's an exciting time to start developing new proposals for scalable experimental violations of the extended church Turing thesis. So let me sort of start wrapping up by the last section of the talk, in which I want to raise the question of, can we hope to come up with a scalable quantum advantage in the NISQ era? So if this direction goes away, and if quantum simulations doesn't seem to be working so far, is there any hope for maybe it's just impossible? Okay, so for that, I think the most important thing is the definition. I think I should say I haven't defined really the NISQ era until now, or the NISQ quantum computations until now, and the only time, so only recently there was a paper attempting to define this, and so let's try to define it in order to try to answer this question. So one particularly important property of NISQ devices is that it's hard to reset qubits. And why is this very important? It seems that reset gates, meaning taking a qubit and putting it to the state 0, to a known state, is crucial for quantum error correction. And the reason is that when you have noise, entropy makes the state, entropy accumulates, and you have, in order to perform computation for a long time, you have to cool down the system. So you have to take computation, you take entropy out, and this is done by reset gates. So if you can't do reset gates, it seems like this is a very serious problem, and people thought, or it makes sense to think, that maybe the ability to do reset gates is sort of the distinction between NISQ era and the fault tolerance era. Okay? So with this in mind, you can think of NISQ devices as those devices which start with zeros and have errors in them, but they're reset-free quantum circuits. There's no reset gates here, just unitary gates and errors, noisy state preparation, noisy unitary gates, noisy measurements at the end. Okay, so that could be a model for NISQ devices. So already very long time ago, it was realized that that with those devices, as I already said, entropy increases, information decreases exponentially in the depth, and therefore you can actually, the result is meaningless after log depth. So essentially, such circuits with noise can be simulated by log depth ideal quantum circuits. going beyond log depth doesn't make sense. Okay, so that sort of makes us wonder if NISQ is very powerful because it only goes up to log depth. But recently, in this paper of Chen, Kotler, and Huang, here, they notice that it's not just log depth circuits. We actually have at our hand also classical computers interacting with those circuits. So they define NISQ in the following way. You have a classical computer, and that's interacting with this noisy quantum device. And this guy works in polynomial time, and this quantum device is noisy. And so this is how they define NISQ, the class of problems solvable by BPP, classical computers, polynomial time, with access to noisy quantum circuits without fresh qubits. And the question is, can we hope for a symptotic quantum advantage with NISQ devices? Okay, so note the dependency on the noise model, but I won't go into this here. And the surprising thing is that Shor's algorithm lies in this model. So let me explain why. It's not exactly in this model, it's in quasi-NISQ. So NISQ devices are polynomial time log depth. I'm talking about quasi-polynomial time, but I think in spirit it lies in NISQ, and there's a technical thing that would bring it to NISQ. So why is that? Let me explain that, and that will be the last slide, I think. Okay, so think of this model. So in fact, this paper defining NISQ is what made us realize that this is true, but we've already known that 20 years ago. So this is a combination of two results. One is that a result by Cleve and Watwus that says that factoring, the quantum algorithm of Shor, can be performed by BBP with access to log depth quantum circuits. So not noisy, but log depth quantum circuits. So that was known. And then the problem is that there is noise. So now you have to compute these log depth quantum circuit on a noisy device. So what do? You recall an even older result that says that, in fact, if you have only log depth ideal quantum circuits, you can simulate it by noisy quasi-polynomial size circuits with no fresh qubits, as long as the error rate is less than the threshold for fault tolerance. Let me say that again. If you have log depth quantum circuits, you can replace them by noisy circuits with the model of the NISQ era, no fresh qubits.
This is
If you had fresh qubits, then obviously this would be in NISQ, but it's not the definition of NISQ. The whole point was that there's no fresh qubits. So this is sort of their choice of the definition of NISQ, no fresh qubits. Because if you have fresh qubits, then what prevents you from doing fault-tolerant quantum computation? Okay, so why is that? Essentially, the idea is perform fault-tolerant quantum computation as if you had fresh qubits, but you don't. But since your qubits don't degrade much in this log time, you can actually prepare many qubits. If you needed a fresh qubit at time t, you can prepare many fresh qubits at the beginning and sort of distill them without additional fresh qubits, sort of pick majority of majority of majority of majority. And it turns out that you can maintain a single fresh qubit for every, if you started with, at time t, if you started with 3 to the t fresh qubits at the beginning, without introducing more fresh qubits. So you can basically simulate fault-tolerant computation with no fresh qubits as long as you have only log depth. Okay, so this means that basically Shor's algorithm is in this model, and then one can say, okay, let's just do Shor's algorithm in the NISQ era before we have fault tolerance. And I think that raises the question of what is this definition good? The point is, I think that the fresh qubits is not the right distinction between NISQ era and the time in which we'll have fault-tolerant quantum computation. In fact, probably the real distinction is much more complicated. It's the fact that the noise is much larger than the threshold, as well as the fact that we don't have access to unboundedly many qubits. So I think the definition for NISQ is still missing. And so there is a very big question, not only of whether we can actually see quantum advantage in the NISQ era, but even what is the NISQ era. And I'm ignoring these last two remarks and just leaving this question, is this definition good? So let me just end with asking, could the violation of the extended Church-Turing thesis be demonstrated in NISQ with error above the threshold in very noisy devices? Can such violations be defined based on quantum simulation? So can we actually come up with ways to actually show quantum advantage in with what we have today? And maybe more generally, have we actually probed the high complexity regime of quantum mechanics, that regime which we believe exists, that is capable of actually performing highly complex quantum evolutions that involve macroscopic entanglement? Do we have any proof that this phase exists? And I would like to say probably not yet. Thank you.
Is it known whether like the cryptographic quantumness, like the Mahadev protocol, fit in this, like the Mahadev style? Oh, there. Oh, okay. Thanks.
Okay, thanks for the great talk. Is it known whether the cryptographic proofs of quantumness, like the protocol of Mahadev et al., would also be within NISQ by this definition?
No, I don't know.
Okay.
That's a good question. I don't know.
Hey, so I was wondering, what about simpler quantum models like boson sampling? Like, do you think there is a hope for demonstrating quantum advantage in those?
Yeah, so boson sampling is, where is that? Yeah, what about boson sampling? Here. So there has been a follow-up on our paper by Oh, Jiang, and Pfefferman just I don't know, 2 months ago, showing that some versions of boson sampling can also be simulated. But I think, as I said, there are caveats to our result. I think that in spirit, and also to the result on which we rely on, the Gauss-Duan result. In spirit, it says that, I think that people believe that this basically says that this approach of sampling, the way it is done in boson sampling and in random circuit sampling, is probably not the way to go. But we left a lot of things untouched. For example, the particular distribution from which Google derives its random circuits, we don't know how to handle it. We know how to handle Haar-random unitary gates and various other distributions which are sufficiently random, but it's very hard to analyze the case by case. And Google's particular randomness, we don't know how to analyze. We analyze something very similar to that. So you could, I mean, it's a game of you know, a mouse and a cat, but it's not. So I don't think it ends. But I think that in spirit, it's a very strong evidence that there is a problem in this. So in particular, the hardness conjectures based on the anti-concentration go away. We actually can prove that those conjectures, those mathematical conjectures, no longer hold. So in fact, the basis for the hardness, for the belief that these directions should be hard, is very shaky.
Cool, thank you.
Yeah. So I have a question. Can you go to the microphone?
So, you know, all all this is based on assuming something about the way the noise in the quantum systems. So do we know if our noise kind of just assumptions are correct or any evidence?
I think this is a great question. This is really a great question. Where's that? Is that here? No. I have a reference for, okay, I don't find it. But I have so basically, the behavior, the nature of the noise is extremely important. And you can think of, okay, so this random noise is very detrimental. It's very bad. It just increases the amount of entropy, and you can't do anything once the entropy increases. But in fact, if you look at what condensed matter physicists do in their experiments, clearly this is not the kind of noise that happens there, because something is there in the lab. It doesn't just becomes completely random after a very short time. That's not the situation. So there's a lot of symmetries. There's a lot of things that you can say about the noise. And it might very well be that the noise models, the right noise model to handle is something that is far more stable, or keeps the quantum evolution far more stable. I just want to say theoretically, it's extremely important. I mean, the results that I was talking about talk about models of noise that could be very general but increase the entropy. As soon as you go to models in which you don't increase the entropy, then those results are no longer there.
Any other questions? Well, let's give Dorit another big round.
Thank you very much. Thanks.